All right, so welcome back to the OneClass channel. Again, my name is Joey. I'm going to be your chemistry teacher for this session. So here at OneClass, if we're tuning in for the first time, what we're doing here is that we're verifying solutions, kind of in math and in chemistry, both in the secondary school level, so the high school level, and as well as in the university and college level. So particularly in this video, what we're going to do is we're going to work through hopefully 10 questions in the university level. So this is in your general chemistry university level 1, your one course, or in your organic chemistry course. So these are problems that you typically find there. Again, my name is Joey. I'm currently an Ontario secondary school educator, and my teachables are indeed one of them is in chemistry. So hopefully, with my background in that one class here, what we're going to do is we're going to verify these solutions together so we have the best resources moving forward. So let's get started on today's problems here. So what we have here today is our first question that he's asking is rank these systems in order of decreasing entropy. So from largest entropy to the biggest entropy, the largest entropy to the smallest entropy. So let's see. Refresh the page here for a sec. So I'm ranking them from basically largest. Writing is not the best here, sorry. So largest entropy to smallest. And then what we're going to do is, and then you could rank them as equivalent if you overlap them. Okay, so we're given these guys here. So we have 1 mole of nitrogen dioxide at 273 Kelvin and 40 liters. We have a mole of helium gas at 273 Kelvin, 20 liters, and then basically a combination of these guys here. So what we have to do is, if we want to figure out this problem, what we're going to have to do is look at these specific factors. So we're going to look here first at the moles. So first, we're talking about the moles, or how much amount of gas there is in the chemical in the compound. So amount. So this here is measure of gas. So the moles is our first factor. Our second factor is actually the type, or what chemical it actually is. So type here would be chemical structure would be another factor. Thirdly, we have, as you can see here, we have temperature, right? Temperature is also a factor. And then finally, volume is a factor. 40 liters, and some of them are at 20 liters, right? So volume here is our fourth factor here. So knowing these four factors, how are they related to entropy? So let me look at this here. We have moles here. So moles here is the measure of gas. So if you think about moles here, the more moles you have, the larger entropy is going to be, because the moment I break up that system, I'm going to have more energy that's being released, or it's going to create more disorder, right? So this is actually proportional to entropy. So I'm going to say here, I'm going to do a little fish sign and say this here is proportional to S here, or delta S here. So therefore, as I increase my moles here, I'm going to increase the amount of entropy that's given. Chemical structure. So this is looking at nitrogen gas, look at helium, nitrogen gas, liquid helium, and so on and so forth. So chemical structure, basically I increase the amount of entropy if it's the bigger the compound, right? So the bigger or the larger, it's also proportional to delta S, right? So a larger chemical structure will give me a bigger entropy, change of entropy. Same with this temperature here. If you think of temperature and think back to particle theory, we're given the higher the temperature, the higher the moving of molecules, right? So our elements, our molecules are moving faster because there's higher temperature, right? So the higher the temperature, the higher the entropy, right? Because again, if I were to the amount of an entropy is just the amount of disorder, right? The higher, the faster the molecules are moving, the higher the entropy, obviously. And then finally, for volume, volume is also increasing entropy as well, because I have more space, right? This is talking volume. When we're talking about volume, we're talking about space in which the molecules are kind of entrapped in, and the higher the volume, the higher the entropy as well. So given these relationships, we can actually solve this problem here. So if you look here, their solution that they wrote here is that 1 mole of nitrogen dioxide at 273 at 40 is going to be greater than 1 mole of nitrogen gas at 273 and 40. So this solution here is correct. So the reason why that is that I'm going to prove that the first statement is correct by simply just saying, drawing out the chemical structure. Remember, if I'm looking at the moles here, I have 1 moles and 1 moles, so they're exactly the same amount of moles, same temperature, 273 Kelvin, 273 Kelvin, and then 40 liters and 40 liters. So all three of these guys are the same except for the chemical structure. So we're comparing here NO2 versus N2, right? And as you can see, NO2 by atomic mass and by molar mass is the bigger structure, right? And I told you that the larger structure is proportional to the entropy here. So therefore, this here is the highest. It's going to create the most amount of entropy in our system here. So I'm going to write number 1 here. Our rank 1 here is 1 mole NO2 gas at 273 Kelvin in 40 liters. So this here is our first one here, and then therefore, if this is our first one here, then the second one must be our nitrogen gas, right? Our nitrogen gas here will be our next kind of next second largest, you can say. So this would be 1 mole of N2 gas at, again, same temperature, 273 Kelvin in 40 liters. So looking at these two, again, these two are the biggest structures, right? Nitrogen and nitrogen dioxide are the biggest structures. And then we're going to look at we're going to look at the next biggest one. The next biggest one is going to be helium, right? Helium, liquid helium, helium gas, and helium gas. So all of these guys are helium. And then we have to look at our concentrations, right? Or sorry, our moles here. And as you can see, this 1 mole here and this 1 mole here would be kind of the same molarity here. And as you can see, the only difference between these two things are its volume, right? So as you can see, this one is 20 liters and this one is 40 liters. And as we said already, if we increase the space in which the molecules are trapped in, we're increasing the amount of entropy. So therefore, our rank 3 would be rank 3. Our number 3rd would be 1 mole of this would be helium gas at, this would be again 273 Kelvin in 40 liters. And the number 4 would be again 1 mole of helium gas at 273 Kelvin in 20 liters. So again, these two would be my next kind of two separate things. And then finally, if I have so this here is good, this here is good, this one is good as well, and this one is good as well. So now we have to look at the half moles, right? The half moles here are half mole of helium gas and half mole of liquid helium and half mole of helium gas here. So I'm going to compare the helium gas and the helium gas. We know for a fact that the liquid helium here is going to be the lowest entropy because liquid here moves slower than gas, right, according to particle theory. So we're going to look at basically this half here and this half here. And as you can see, the only thing that's changing between half mole of helium gas at 273 Kelvin at 20 and this one here, half mole of helium gas at 100 Kelvin and 20 liters, is the temperature, right? So temperature here is from 273 to 100 here. And as I said before, temperature is proportional to our entropy, right? As I increase the amount of temperature, I'm going to increase the entropy as well. So number 5 is going to be, the next largest one will be half a mole of, this is also helium gas. This would be at 273 Kelvin, and this was going to be in 20 liters. In 20 liters. And number 6 is going to be half a mole of helium gas at, this would be 100 Kelvin in 20 liters. And finally, the only one we have left, we have 1, 2, 3, 4, 5, 6, 7 is going to be the liquid, right? And as I said before, the liquid guy here, the liquid helium here is going to have the lowest amount of entropy because of its state, right? All of these guys are gases here, and this one here is a liquid. And as we know here, liquid moves much slower than gas here, because according to particle theory. So this here is going to be an order from increasing to decreasing entropy, right? So this here is going to be, let me do this in blue here. So this here is, let me put a line here. This here is increasing entropy. Delta S is going to increase here. So delta S, this is most or greatest or largest, and this is the smallest here. So this here is going to be the order, and this here is our answer. And I believe they also got the same same solution here. And they even specified here, at the same conditions, 1 mole of nitrogen dioxide can be more disordered than 1 mole of N2 or He because it contains 3 atoms, right? So again, the larger the chemical structure, the more disorder can contain. And this here, it says in 273 and 100 Kelvin, half mole of helium gas at 100 K and 20 liters has less entropy because the lower temperature the gas molecules are not as energetic. They don't possess enough kinetic energy, and they don't occupy that many energetic states. Or you can just simply say there's there's more entropy because there's more kinetic energy that's being placed into the system. And as we know that, here Gibbs free energy and entropy are also related, right? Delta G equals delta U minus T delta S here. And liquid, again, has lower entropy than gas, which is correct because of particle theories, because liquid particles move slower than gas particles. So this here solution is correct. It's a good analysis here. Okay, let's do number 2. Again, these ones, I don't think I can actually finish like 10 problems per hour, just because most of these questions are, again, on the higher level. So it's a lot harder for me to even explain this to you guys within the span of 5 minutes per question. So I might actually have to end up doing like 5 to 8 problems per hour. But that's totally fine. We're going at our own pace here. So it says, what substance would you need to add CH3COONA to form a buffer solution? So I'm given here CH3 COONA aqueous, and I want to find what substance to add to this guy to form a buffer solution. So this here is more this here is a lot more conceptual, in the sense that we're not given our concentrations, but we're just given this here. This guy here is sodium acetate. This here is sodium acetate. And what we know is that if we want to find a buffer, how do we create a buffer? Well, there's kind of 3 ways to form a buffer here. So we can either do one of three things here. So we can have either a strong acid or actually a limiting strong acid plus weak base. So limiting strong acid plus weak base. 2 is limiting strong base and weak acid. Strong base plus weak acid. And then thirdly, we can also use conjugate acid and conjugate base, right? We can use our conjugate acid plus conjugate base. And how do we know this? Well, we know this through our Henderson-Hasselbalch equation, right? So we know that our Henderson-Hasselbalch equation, this in blue. So Henderson-Hasselbalch says that pH equals pKa plus log of our base over our acid, right? And basically what we want to do is, when we want to find the buffer, we want to know that it's going to be at half equivalence point. pH equals pKa is the buffer region, right? So again, with the buffer region, we want to know it's plus or minus 1 pH value. So this ratio has to be about a ratio of 10 in order for us to solve this first. But because this is a conceptual question, this is asking us, what we have first is CH3CONA, and this is sodium acetate. So we know that this here is our base, right? So we're really focused on just simply this part here, the log of base over acid here. So we have our base already. So log of our base, which is CH3COONA. We want to find what acid should we put in this. So we need an acid first. So to create a buffer, right? Because according to Henderson-Hasselbalch, we need both a base, either a limiting strong acid plus a weak base, strong base plus a weak acid, or a conjugate acid and conjugate base. So you can think of this here. NaF is a ionic compound, so it doesn't work. CH3COH, this here guy works. NaCl is an ionic, so it doesn't work. NaOH wouldn't work because I'm adding a base and a base together. NH3 is also a base. HCl here is a weak acid. And so basically the only solution here is B here. And this is acetic acid because I'm following rule 3 here. Rule 3 here is it's acid and conjugate base. So this here, this here would be, I'm going to rephrase this as either A plus CB or B plus Ca, meaning that acid plus conjugate base or base plus conjugate acid. And in this case specifically, we have base and conjugate acid, right? CH3COONA is indeed a base. So what we need is this conjugate acid. And we know the conjugate acid of CH3COONA is indeed acetic acid, which is CH3COOH. So in order for me to form a buffer, I'm going to need CH3COOH, CH3COOH here. So this guy here is my answer. B here is my answer. And as you can see, the solution is also correct. To have a buffer, you would need a CH3COO minus and its conjugate acid CH3COOH. So if I were to be really, really specific about this, sodium acetate actually dissociates first to form our acetate ion, right? So we have CH3CONA. It's going to dissociate to form CH3CO minus plus Na plus here. And this guy here is going to be the product, is going to be the reactant in my acid base equilibrium. So CH3CO minus plus H2O is going to be in equilibrium with our acetic acid CH3COH plus OH minus here, or sorry, plus OH minus here. And as you can see here, this here is our base. So here is our base, because again, I'm donating a hydrogen here to, I'm accepting a hydrogen here, which means this here is our conjugate acid. So again, I want a base and conjugate acid, so CH3COOH is our answer here. So solution here is correct. Good analysis. Okay, number 3 is asking us which electron transition produces light of the greatest frequency in the hydrogen atom. So I don't know what this IS here stands for. Is it, maybe I'll click this image to download and see if there's a better explanation for this. Just give me a second. 220. Oh, it's 2-1s. Okay, so it's not IS. Okay, that makes sense. So it's 2 back to the ground state. So I thought it was talking about LS. So this is actually a 1 here. So that makes sense. Okay. So let's click 3. So this is 3. So it says, I want the produce the light of the highest frequency. So highest frequency of light produced in the hydrogen atom. And then I'm given 4 options here. So A here is 5p to 1s, B here is 4p to 1s, C here is 3p to 1s, and finally D here is 2p to 1s here. So what is our highest, which one would be our highest highest frequency of light produced in the hydrogen atom, right? So let's look at this here first, and we're looking at basically our energy levels, and it's all basically it's all going to emit energy to go back to the ground state. So if I were to draw out kind of the energy level diagram for this, I'll draw it for only A because they're all very, very similar here. This is delta E here. So you can think of this here as this state here would be a 5p state, and this here would be the 1s state, which is our ground state. It's going to emit here some type of energy, right? Some type of energy here is going to be released for us to and then in this energy, while it's being released, it's going to have a specific frequency of light that's being produced, right? So this here is going to emit some type of frequency. So this here, I'm going to get some type of energy that's being released. So this works for the 4p, for 3p, and for 2p. It's asking us which is the highest frequency of light. So if I were to look at our equations here, what we kind of have to first find out is our relationship between the energy levels and how much energy it's going to be released. So let me bring you back and recall that we know that we have a couple of equations that we know. So we know here that E energy equals hc over lambda. That's a delta, sorry, over lambda here. Meaning that our energy equals our Planck's constant times our speed of light. Again, h here is our Planck's constant, c here is our speed of light, divided by our wavelength here. And we know that also, we know that because E here equals hc over lambda, we also know that our wavelength, or lambda, equals our speed of light divided by our frequency, right? So these two are things we know, right? These two are kind of equations that we learned either in physics or in chemistry as well, because actually we probably had to reorganize this. So we probably knew that V here equals F times lambda, and then therefore lambda equals V over F, right? So this here, lambda would equal, lambda would equal V over F here. So maybe it's something that you might learn from physics or something like that. V and C here are interchangeable. So let me for this problem specifically, so let me rearrange this. So we know that this is equation 1 and this here is equation 2. What we can do is actually sub 1 into 2 to find our relationship, right? So in order for me to do that, I'm going to have, say, E equals hc over c over f, right? Or you could rewrite this as hc times the reciprocal f over c, right? And again, the c's here cancel out here, so my energy here is simply just at h times f here. So this here is going to be my proportion. So energy equals Planck's constant times our frequency, and assuming that they're both traveling at the speed of light here. So this here is actually a really, really good proportion, and really, really good to what we need to know. And if I know that energy equals Planck's constant times f, we know that in conclusion, energy is proportional to our frequency of light, right? So therefore energy here is proportional to our frequency of light that's being produced, which is really, really, really good, because then if I want to know the highest frequency of light, then I'm simply just figuring out the highest, what would give me the highest energy, because highest energy would equal our highest frequency here. So this, I want to know the highest energy released would produce my highest frequency of light. And according to these 4 options here, which one would be the highest energy that's being released? Well, obviously, it would be the one that's furthest away from the ground state, which will be option A here. Because option A, remember, if you look at the electron configuration, this here would be much, 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 much greater in terms of energy than 2p, right? If I were to write out the 1s state, again, 1s is all the way here, and then it's 2s, 1s2, 2s2, 2p6, 3s2, 3p6, and so on and so forth. And as you can see, the higher the number here, the higher the principal quantum number, because here n equals 5, this is n equals 4, n equals 3, and n equals 2. The higher the principal quantum number, the higher the energy that's being, the higher the energy level, and the greater amount the energy will be released. So therefore, it's going to have the highest frequency of light being produced here. So number 8, option A is correct, and they wrote here option A is correct as well, and they explained it as the energy of emitted light by the electron transition is again, these are not complete sentences, so it says here, it doesn't really, it says solution, the explanation is really bad. So I'm going to say solution is correct, analysis is incomplete. And I'm going to basically stay here. We know that E equals hc over lambda. And we know that our speed equals our frequency times lambda here. So therefore, E equals h times f. So we know that energy is proportional to frequency. Therefore, the higher the energy level, the higher the principal quantum number, the higher the energy level, and the higher the energy that is being released. Therefore, increasing the frequency of light that is being produced. So this here is actually the correct, this here would be the correct analysis for this problem. So I'm going to say solution here is correct, but they just had a very, very poor analysis because I think their question was probably cut off by something here. So I'm going to say solution here is correct. Okay, let's look at number 4. Number 4 is asking us draw the final product from the following 6-step reaction sequence. So very, very long question here. So I have, this is an organic chemistry problem here. So let me just draw the structure here. And then I have basically 6 steps here. So I have quite a bit. So first one is NaOCH3. So again, some type of base here. And then I'm going to add an alkyl chain of BRs. Let's 1, 2, 3, 4, 5. 1, 2, 3, 1, 2, 3, 4, 5. Okay, that's good. And then 3 will have NaOCH3 again. 4 would be an a lithium aluminum hydride oxidation, or sorry, reduction. Water, and then some type of ketone with a tosyl group as our catalyst. Okay, so we have a lot of steps here, so we have to break this down into a couple of steps. And actually, for the sake of time, I might actually just look at the solution to just verify that the solution exists, and then kind of reverse work our way back here. So the solution that they provided here is this, but they didn't provide a specific analysis here. So let's kind of work this out here. So the first kind of step here, what I'm doing here is I'm deprotonating something here, right? So in this case, this is sodium. The sodium here is going to deprotonate a specific some type of hydrogen atom. In this case, it's going to actually deprotonate this step here, because this here is the alpha carbon between 2 carbonyl groups. So so if I were to deprotonate this one, I would get a negative. I would get basically a hydrogen would be removed here, and this guy would be kind of a negative. There would be a negative charge on this carbon here. Then our second step, it would actually attack this bromine here, right? I know that this guy here is partial negative, and this here would be partial positive, right? So this guy is going to come and attack here, and then it's going to kick out this bromine here. It's going to form some type of bromine chain. So let me try to draw this out for you. And I don't really want to spend that much time on this question here. So let me see if I can draw this out again. So O, double bond O, bond O, and then I have basically I have 1, 2, 3, 4, 5. So I have 1, 2, 3, 4, and 5, and then and this is actually symmetrical. So I have 1, 2, 3, 4, 5, and then I would have my BR here. And then what it's going to do again, I'm going to then repeat the same process, right? I'm going to again deprotonate a specific carbon here, and I'm going to add add something to it. So I'm going to deprotonate here. I'm going to deprotonate again the same carbon atom here. So one of these guys here is the hydrogen is going to be removed. So I'm going to have a negative charge on here again, and then I'm going to use lithium aluminum hydride to reduce this compound here. So when I reduce this compound here, I'm going to start making this cyclic group here, right? So if I reduce this compound, I'm going to basically eliminate these ester groups here. So I'm going to get basically just let me just see if I can draw this out here. I'm going to remove these ester groups. So I'm going to get something like this. So it'd be a double bond O, and this is simply bond H now. Double bond O, choose bond H, and then I have my the alkyl group here. So 1, 2, 3, 4, 5, and then our BR here. I'm using a water workup here, so this is going to be a substitution between this BR here. So I can simply this here would become a it would do an elimination, and maybe I would actually reduce this bromine into an alkene. So this guy would be removed, and this carbon's also removed here. Or sorry, 1, 2, 3, 4, 5, and this would have a double bond here. And then what it's going to do is going to with this compound here, this ketone here, and with the tosylate group here, it's going to basically form a cyclic group. So let me show you how it forms here. So again, I have here, this is this is a 6-membered ring here with my 2 carbons here. So I have, again, our 2 carbons here and our 6-membered ring. So 1, 2, 3, 4, 5, 6. So this is 1, 2, 3, 4, 5, 6. So this here would become our ring, and this here would become our kind of the acetyl groups here. So this here would be our solution for this problem. So this here is actually the correct solution. Let me see. What this is going to do is actually going to add. I'm going to basically protect these groups with tosylate groups here. So these guys here become I'm adding basically an extra carbon here. So it produces these 2 guys. It's going to bring these methyl groups back here. So I form these 2-membered rings here. So this solution here is correct. And again, this here basically I create a ring with these 6 carbons, and I get the acetyl group with these 2 carbonyl groups here. So this solution here is correct. Good analysis here. Okay, but they didn't really provide analysis, to be honest, and they didn't really write a mechanism, so I shouldn't have written actually a good analysis here. So actually, my bad, my fault. Okay, so number 5 here. So I have this compound. And I have the other one here. It's going to form Br here. Or sorry, I have a methyl sticking out from here. And then I have another methyl group here. And it says here, it's treated with MBS in the presence of UV. So MBS in UV, and then what is it going to do in UV here? So this guy wrote that the bromine is going to attach here. But again, this here would be the incorrect solution. So again, this says here it's not correct, right? So we're thinking of, so again, these here says here you don't have to consider stereochemistry, you don't have to draw each atom, so on and so forth. So this solution here, what they're doing is they're actually going to break down what the mechanism behind MBS here is. It's actually a very complicated radical halogenation step. So I could actually walk this. I can walk this over with you. I really don't want to redraw it. It is pretty complicated. But what it's going to do is this here is NBS, so N-bromosuccinimide. What it's going to do is it's going to undergo radical halogenation. So this HV here is the ultraviolet. It's going to break up this N bond Br bond. It's going to form our NBS kind of. This would be our kind of just our nitrogen radical here and our bromine radical. And what this does here, this radical, what these 2 radicals do is going to break up. It's going to cleave the alkene bond here. So this alkene is going to react with our radical here to form this guy here. So again, I have my hydrogen on. It's going to again basically deprotonate one of these guys here, or it's going to add. Sorry, it's going to add a not deprotonate. It's going to add a positive charge or add a hydrogen to one of these charges here. So as you can see, this is what they did here. The hydrogen charge is now on this carbon here. And what this is going to do, and again, you're going to do then a methyl shift. I believe this would be a methyl shift indeed. And this methyl is going to come and bond here and moving this radical upwards. So let me draw that out for you because this step is a bit more complicated. So this here is a shift, or you can say this in this case, it would be a methyl shift. And why this is a methyl shift is because, again, I have a secondary, this here is a secondary carbocation. What I want to do is I want to make this a tertiary, right? So if I want to make this a tertiary one, it's going to go, again, tertiary is much more stable than my primary here. So I'm going to get double bond here, and then I'm going to get one here, and then the positive charge is going to land here. So this here is actually, no, this here would be a hydride shift, not a methyl shift, sorry. I'm not shifting my methyl. This here would be a hydride shift here. And this hydride is basically from let's see, 1, 2, 3, 4. It's from one of these hydrogens here to make my hydride shift. And then I have my Br, right? Again, I have Br. I still have my Br radical here. So again, this guy here is negatively charged. So let me use my colors again here. So this here is positive. My Br here is a negatively charged. It's going to come and bond to this guy here. So this site here. So I'm going to get my final product here. Looks something like this. And this here is the correct answer for this problem here. So again, Br would not bond here. A lot of students actually fall into this trap because they don't know the mechanism behind NBS and where the carbocation is going to be created. A lot of people just assume it's going to be on this carbon here, but remember there's hydride shifts also exist to provide the most stable carbocation. In this case, the tertiary carbocation, in this case, NBS wouldn't actually depronate here. It would depronate in, again, it would depronate again in this spot and not in this spot here, because this is the secondary carbocation. It's much more stable than the primary carbocation, and then a hydride shift is going to occur to bring this carbocation into a tertiary position for the bromine to then attack and then to form our alkyl bromide here. So this solution here is correct. It's a good analysis because they provided a mechanism behind this bromination here. So let me, okay. So it's asking us now, number 6. It's asking us, click on all the atoms that make up the largest coplanar unit in the molecule below. Okay, so I don't know how we could click the atom. So it's just asking us which are the atoms that make up the largest coplanar unit, right? So I believe it's probably some type of system that they want us to click, but again, we can't click, right? So when we're talking about coplanar units, we are talking about hybridization and Vesper theory. So this is the concept of hybridization and how the geometry affects the chemical structure. So hybridization in the sense that we care about our sp, sp2, and sp3 orbitals here. In this case, we have an alkene. And in an alkene, we have an sp2 hybridization, right? sp2 hybridization here. So I form, in sp2, I form 1 pi bond, right? We know we form pi bonds, or we form 1 pi bonds, and we form sigma bonds as well. So we form pi bonds and we form sigma bonds. All right, that's a theta here. This here would be sigma bonds here. So we know that sp2, and we know that this here is indeed planar, right? So we know that sp2 carbons are planar. So so that's why we care about sp2, because these guys here are going to make up my planar units. So as you can see here, this sp2 carbon and H attached are planar, right? So we just care about basically this double bond here. So knowing that, we can say that our coplanar unit here is, I'm going to actually draw this in, I'm going to use color to help you differentiate these carbons here. So again, this here is CH3. I'm not going to draw all the carbons. It's kind of tedious here. We know that this is H3C. This here would be bond, and then I'm going to write this in blue because this is the carbon that's a planar carbon, and this here is double bond to a planar carbon, and this here would be again H here. This here is H. So let me write this down. This here is H. This here is H, and this here would be H here as well. So again, these guys here are going to be planar, right? Like all the blue stuff here is planar. As you can 1, 2, 3, 4, 5. These guys are all planar. And again, this here is our answer for the first molecule here. So these guys are all planar. And then finally for the second one, I'll draw that out as well. For the second one, again, I have H3C here, again, using some short form. And again, I know that this carbon here is planar because it's involved in the double bond, right? So I have double bond carbon, and then this would be, again, bond carbon, and this one here is not sp hybridized, and this here is H3C. And then finally, I'm going to have, again, I have one carbon here, and then one bromine here. And these guys are all, this part here is all planar as well. And as you can see, this Br is planar, this carbon's planar, this carbon's planar, and this hydrogen is also planar. Because these guys here are indeed, this carbon here is sp2 hybridized. This is also sp2 hybridized. However, these guys here are sp3 hybridized here. So sp2 again is planar, sp3 is tetrahedral, right? So it's not planar. So again, these here, this here is the correct answer. So the solution here is correct. This is a good analysis as well. Let's look at number 7. Is calculate the frequency of each wavelength of electromagnetic radiation. So I want to find the calculate frequency. That's it. So I want the frequency, right? So the first one is 632.8 nanometers. B here is 503 nanometers. C here is 0.052 nanometers here. Okay, so if I want to convert, again, these guys into frequency, how would I do that? Well, I know that my formula, again, this solution here is incorrect because, again, it's very, there's no numbers here immediately, so I can figure out that this solution is incomplete. But I basically want to calculate the frequency of each wavelength of electromagnetic radiation, right? So, in order for me to do that, I know that, again, my speed here, or V here, equals our wavelength, or lambda, times our frequency, right? So if I want to rearrange for frequency, I can simply say frequency equals V over lambda here. And in order for me to do that, I would have to do, again, all of these guys have the same speed, right? These are all traveling at the speed of light. So I can say that the V here is simply just C over lambda. Where C here is equal to 3.00 times 10 to the power of, I believe it's 8 meters per second for speed of light. I'm just going to double check that. And again, you should be given these types of constants on a test given situation. So let's see, 300,000,000 is, yes, I believe it's 3 times 10 to the power of 8. 1, 2, 3, 1. Yes, 10 to the power of 8. Okay, so given that, we can simply just calculate these guys here, right? So for A, I can simply write, if I know this equation here, I simply know that A here is going to equal, F here equals C over lambda. Let me do this in black, actually. Actually, I'll do it in blue, that's fine. F here equals C over lambda. We know that frequency is equal to 3.00 times 10 to the power of 8 meters per second. And this here, because we're in nanometers here, we're going to convert nanometers back into meters, right? So if I want to convert that, I know that a nanometer to meters is 1.00 times 10 to the power of -9. So if I want to convert this here, I'm going to have to write 632.8 times, I'm going to multiply that by 10 to the power, or 1.00 times 10 to the power of -9. So 1.00 times 10 to the power of 9, and then this will give us meters here. I'm converting from nanometers to meters here. And this one will give us our frequency in 1/seconds, and that's going to be in hertz. That's our units for frequency. So I have 10 to the power of 8 divided by 632.8 times 1 times 10 to the power of -9. And this is going to give me 4.74 times 10 to the power of 4.74 times 10 to the power of 14 here. And this here, let's see. Yes, 4.74 times 10 to the power of 14 hertz here. And this is my frequency for my first, for A here. So let me see what it would kind of, I don't think I can show you in terms of order of magnitude for frequency. Maybe I should give you a kind of a frequency here. But if I'm going to take this off Wikipedia and show you here. But this is just the order of frequency, and as you can see, 10 to the power of 14 here is equal to electromagnetic. So this is visible light from red to violet, and as we can see, this is the wavelength of red light. So this is very, very close here. 4.74. This is about 474 THz would be 10 to the power of 14, and this is visible light. So we can see that it's the wavelength of red light. So this solution here is correct. So that's just kind of double checking in terms of a real world example how this would play out. And again, I can solve for B and C, right, in similar fractions here. So B here, again, I have F here equals 3.00 times 10 to the power of 8 meters per second. I can divide that by our wavelength of, for this here is 503 nanometers. So I'm going to write here 503 times, basically times 1.00 times 10 to the power of negative 9 would give me meters. Plug that into my calculator, and I would get, let's see, 10 to the power of 8 divided by 503 times 1 times 10 to the power of negative 9. This would give me a value of 5.96 times 10 to the 14. 14 hertz. And again, this is a wavelength of maximum solar radiation, right? So again, solar radiation would probably be very close to here as well in terms of our 10 to the 14. So again, it should hover around the 10 to the 14 electromagnetic kind of for wavelength of solar radiation. So it hovers around the same kind of frequency here. And finally, my last one here is wavelength contained in medical x-rays, right? So medical x-rays will be much, much smaller. So I have 3.00 times 10 to the power of 8 meters per second. I'm going to divide that by, again, I need to convert nanometers, 0.052 nanometers into meters, right? So again, 10 to the negative 9 meters is my conversion factor. So again, I'm inputting this into my calculator, 3.00 times 10 to the 8 divided by 0.052 times 1 times 10 to the power of negative 9. And this value would give me 5.769 times 10 to the 4 times 10 to the 18. 10 to the 18 hertz here. And to the 18 hertz would be here, right? So it's almost actually a gamma ray. A gamma ray is 10 to the 20, and this one would be very, very close to what this is. And wavelength of X-rays is from basically 10 to the 16 to 10 to the 18. So this here is a correct solution here. So this solution here is correct, right? These guys here are my 3 solutions for A, B, and C. This is A, this here is B, and this here is C. And again, this solution here is incomplete. So I'm going to write solution is incomplete. And then right here for A, I'm going to write F here equals C divided by lambda, which would equal 3.00 times 10 to the power of 8 meters per second divided by our wavelength, which I have to convert from nanometers, so 632.8 times 10 to the power of negative 9 meters. And this would give me a value of 4.74 times 10 to the power of 14 hertz here. And this here is going to be the solution for basically A, B, and C, right? So B here would be the exact same thing. And I would just change the numbers as well. So A, B, and C here, I'm just simply changing these wavelengths, right? So this wavelength is different because this here is 503, and this one would be 0.052, right? 0.052, and obviously I get different wavelengths. So this one I would have gotten 5.96 times 10 to the 14, and this one here is 10 to the 18, and this here is 5.77. And solution is incomplete. And then we can say we can solve for the frequency of the given wavelengths using the equation And then we can say here, speed of light or speed equals our f multiplied by lambda, which is our wavelength. So therefore, f equals c speed. In this case, it would be c equals 3.00 times 10 to the 8 meters per second for speed of light in a vacuum times r, or divided by, sorry, by our lambda, which is our wavelength here, wavelength, and this is in wavelength in meters. So that's going to be our solution here. So solution is incomplete. So we can say this solution is incorrect because, again, it's a very incomplete solution, and these here would be the numbers for this solution here. Solution is incorrect. And then finally, I'm going to do one last question for the day. I have 7 more minutes. I'm going to see if I can solve this problem here, and we will be finished for today. So this is question number 8. It's asking us, a set of 3 nucleophilic displacement reactions is shown below. Which reaction ABC proceeds the fastest? Which one is the slowest? And this is an SN2 reaction. So I have some sort of cyclohexane with X here, and then I have NaCN, sodium cyanide here, and then with a methanol solvent, and then this will be an SN2 reaction. So basically, the product here is I would get my CN here. So it's asking us which reaction ABC produces is the fastest. So let me write this down. So if A here is X equals F, B here is X equals BR, and C here is X equals CL here. So which produces the fastest? So let me show you a periodic table, and I'll use the trends of the periodic table to solve this for us. So we're comparing fluorine, bromine, and chlorine, right? And they all exist in our halogens here, right? So fluorine, chlorine, bromine, which one would have the greatest electronegativity difference or greatest dipole moment between carbon atoms, right? So if I erase this guy here, and I replace this with a carbon, because we know that this here is simply just a cyclohexane. This here is a carbon atom, right? And it's going to be bonded to CX here. So if X here is a halogen, I know that for sure this will have a partial negative charge. And this here would be a partial positive charge, right? So I have a net dipole moment that's going out this way here. So if I change this guy here, I'm going to have this here is a C bond F, this here would be a C bond BR, and this here would be a C bond CL, right? And which of these guys have the greatest electronegativity difference? Well, fluorine's here is the highest electronegativity difference, right? If I look at my periodic table here, fluorine here is the smallest in terms of atomic radius, but it is the highest in terms of our electronegativity. And we know that our trends based in, and if you remember high school, the trends of our periodic table, as I go across my periodic table, I'm going to increase in electronegativity, and as I go down, it's going to decrease. So fluorine being my most electronegative ion means that Cl will be my second highest and bromine will be my third highest. So therefore, C bond bromine is my strongest bond here. This is a very strong bond. Then chlorine is next, right? Chlorine comes right after, so this would be the second strongest. And then bromine here would be my weakest. So obviously the weakest bond is going to be then going to be substituted first, right? So again, this B here is our answer. So it's going to be fastest when X equals BR, because BR minus is a good leading group because of the lack of the electronegativity difference between carbon and the bromine. So this solution here is correct. And what I'm going to do is I'm going to draw up the mechanism for you for this SN2 reaction. So I'll show you how this goes out. So if X is BR, like stated here, I have NaCN and the methanol solvent, and I would get, so first what's going to happen here, this is a SN2 reaction. So again, substitution, a nucleophilic, and this is a bimolecular reaction here, SN2. So let me write this out. So Na plus, and this here is Cn minus. Here, what it's going to do, this guy here is going to come over here, because it's attracted to this positively carbon, right? I just told you that this guy here has a dipole moment, right? And it's going to come over here. Actually, I'll draw some black here. It's going to come, this negative is attracted to this carbon here. It's going to come here and kick out this bromine here. And then I'm going to get first basically a a bromine that's left out first. So this here would be a positive charge here, and then this guy here would be a Br minus, and this CN is going to come and bond to this guy here, and I'm going to get bond CN, and this here is my correct answer. This actually all happens in one step, by the way. So in reality, it actually happens because SN1 is a one-step reaction. In reality, this all happens in one step. So this here, CN comes to attract to this carbon and then kicks out this bromine here. So this you're going to get a backside attack, and you get CN here. Backside attack, inversion of stereochemistry, SN2 nucleophilic substitution. Solution here is correct. And again, F here is, again, the poor leading group, because, again, very lot in terms of electronegativity difference, because, again, fluorine is the highest electronegativity, and then it would be chlorine and then bromine as well. So, again, leaving group depends on the rate of reaction, which is very, very, very true here. So solution here is correct. Good analysis as well. So that's going to be it for my video for today, for the live stream today. Again, thank you so much for watching and tuning in. If you like these videos, definitely go to, these videos are already, will be recorded and will be posted onto the YouTube channel at youtube.com/OneClass, and you can check out all the solutions that I've done over there. Again, my name is Joey. I stream math on Monday, Wednesdays, and Fridays, and chemistry on Tuesdays and Thursdays, so you come and check me out. Again, thank you so much for watching. Stay safe, stay healthy. Have a great day. Take care.